Of the four known forces, one of them stands out as having some unique properties. I've spoken in another video about the manner in which the weak force only interacts with particles of a certain spin configuration and antiparticles with the opposite spin configuration. But in this video, I want to talk about the manner in which particles decay via the weak force. Now, there is an extensive history of how this has been observed that long predates our current understanding of the universe, but I'll explain the phenomena strictly in terms of the Standard Model. So I made another video that introduces the Standard Model, but let me remind you that there are three forces that are understood in the quantum world. They are the strong nuclear force, the weak nuclear force, and electromagnetism. Each force is transmitted by one or more particles called bosons. For the strong nuclear force, this particle is the gluon. For the weak nuclear force, they are the W and Z bosons, and for electromagnetism, it's the photon. So let's see what happens when a particle emits another particle governed by the rules of each of these forces. So what would happen if a particle, say a top quark, emitted a photon? Well, as we can see in this diagram, you start with a top quark, it emits a photon, and it continues along as a top quark. The particle doesn't change its identity during the emission. Now, if you're a physics-minded individual, you'll probably be wondering about energy and momentum conservation in that interaction. This requires that the top quark before the emission have a mass that differs a little from the number you can find in the textbooks. This is one of those things that is allowed under the laws of quantum mechanics, and you'll have to trust me on this. If you want to explore this on your own, Google the term virtual particles. Now, getting back to the decay, I want to redirect your attention to the fact that before and after the electromagnetic interaction, the particle is the same. Now, let's look at what happens during a strong force interaction. The same top quark might emit a gluon and would continue on as a top quark. Because the gluon carries color, which is what physicists call the strong force charge, the top quark will change its color, say from red to blue. And if you want to learn more about those details, my videos on quantum color and the strong nuclear force will be helpful. However, the key point here is that the particle before and after the gluon emission is the same particle. But let's see what happens when a particle emission occurs that is governed by the weak force. There are two particles that transmit the weak force, the W and the Z bosons. So let's see what happens for the Z boson. When a top quark emits a Z boson, it stays a top quark. Basically, it's a lot like the electromagnetic emission of a photon. Nothing weird there. But when the top quark emits a W particle, something very different happens. Before the emission, we have a top quark, and after the emission, we see a bottom quark and a W boson. The weak force has changed the identity, what physicists call the flavor of the particle. This behavior is unique to the weak force, and we call this phenomena flavor changing. While this property is unique to the weak force, it is not unique to the top quark. A bottom quark can emit a W boson and make a charm quark, and a charm quark can emit a W boson and make a strange quark or a down quark. On the lepton side, a tau lepton can emit a W boson and make a tau neutrino, and a muon decays by emitting a W boson and making a muon neutrino. There are many ways in which quarks and leptons can change their flavor, and it only happens when the weak force is involved and only when a W boson is emitted. So that last statement is interesting. Why is it the only flavor-changing weak interaction is the one with a W boson? Why is there not one with a Z boson? Well, let's explore what that would look like. So the Z boson has zero electrical charge, so that means when it's emitted that the emitting particle can't change its charge. The top, charm, and up quarks all have the same electric charge, specifically plus 2/3 that of a proton, while the bottom, strange, and down quarks all have the same charge as well, this time with a charge of minus 1/3 that of a proton. The three leptons, the tauon, the muon, and the electron, all have a charge of -1. I already said that the interaction in which the top quark emits a Z boson and stays a top quark is okay. And this is true for all of the other particles as well. But what about a case like having a top quark emit a Z boson and become a charm quark? That seems like it would be possible, but is it? Scientists have a name for this. They call it a flavor-changing neutral current, or FCNC for short. Flavor changing comes from the fact that the particle identity is changed, and neutral because the particle charge is unchanged. So have FCNCs been observed? No. And that was a pretty mystifying thing until 1970, when Sheldon Glashow, John Iliopoulos, and Luciano Maiani were able to show that flavor-changing neutral currents were forbidden if quarks came in matched pairs, one with a charge of plus 2/3 and the other with a charge of minus 1/3. That's why scientists were pretty sure that the charm quark existed before it was discovered in 1974, and that the top quark existed before its discovery in 1995. Since flavor-changing neutral currents are essentially impossible in the Standard Model, there's a cottage industry looking for them. If they're observed, that is a surefire signature that something new has been discovered. Unfortunately, so far, no luck. But the flavor-changing properties of the weak nuclear force are very interesting and are probably telling us something profound about the universe. The question, of course, is just what is that message? I don't know, and well, neither does anyone else at this point. It's just one more mystery that needs some bright young mind to solve. So what about it? Are you up for a challenge?